it's immodest to say that that's not it. There's one crucial difference between the previous era and this one, and that is that our ancestors, just one generation back, had higher dimension operators to stare at. They had seen the weak interactions. There was some non-zero higher dimension operator that was telling us about the existence of some scale, and so there was positive hints for what the physics was. You don't need that much. A few numbers is all it takes. You know, the theoretical consistency is such an incredibly strong constraint that it eventually led people to the right theory. What are the hints that we've had in the last 30 years in physics beyond the Standard Model? All of the hints that we've had are to explain the absence of things. Okay? We've been trying to explain zero in more and more interesting ways. Why are there not large radiative corrections to the Higgs mass? Why have we not seen deviations in flavor physics, electric dipole moments, baryon number violation, and so on? Okay? So now it is remarkable that even trying to explain zero focuses your attention on a relatively small class of theories. But it shouldn't be shocking that it doesn't tell you specifically exactly what it is that you should be looking for. And it is perhaps unfortunate that such a squishy criterion as naturalness should be the thing that's been driving the field. But it's the only criterion that we actually have had in the absence of any actual number that we really have to explain associated with physics nearby. This idea of naturalness has been correct in the past. This is not some random principle that was pulled out of our ass, that this is the first time it's been tested. A number of times in the last century, questions of the same character as a hierarchy problem came up, and those questions had solutions of the character that are of the sort that we're talking about now. But from day one, yes, certainly. I mean, there are some famous ones. Maybe the most famous one is the problem of the classical self-energy of the electron. So Abraham and Lorentz and people in the late 1800s and early 1900s were very confused about the infinite self-energy of the electron. So they made a little model. They said, let's say the electron's a little shell, and they calculated the energy stored in the electric field. And if you do that little calculation, and you say, well, what size do you have to give the electron? So the energy stored in the electric field is comparable to mc squared. You get some number. It's called the classical radius of the electron. So what they tried to do is build a theory where the electron had a structure at around that size. They failed miserably over and over and over again. That was the Technicolor of the early 1900s, really literally. Really literally. The idea was that it was composite at exactly the scale that you would expect from this estimate. The right answer was much more radical. The right answer was relativity and quantum mechanics and particles and antiparticles and the whole picture of this virtual cloud surrounding the electron.
And speed. And speed.
And many other things.
Right. If that had been a scalar, it wouldn't have worked.
True. But the point I want to emphasize is that actually in that case, not only did just because they failed to come up with the right model, their basic idea was actually exactly correct. New physics did show up by that scale. In fact, it showed up much earlier than it had to. The Compton wavelength of the electrons and positrons that are outside the electron are alpha inverse bigger than the classical electron radius. At scales 137 times larger than they absolutely had to. The new physics came in. That's exactly the problem. So that's exactly why I wanted to make this point. So that's the most famous example. There are other examples. The splitting between the charged pion and the neutral pion. Okay, that's something where if you the charged pion is charged, so you draw the hierarchy problem diagram for the charged pion, exactly the same diagram we draw for the Higgs. You get freaked out that there was going to be a massive radiative correction to the mass of the charged pion. You say that some new physics has got to come in by some scale to save it. It comes in just where it's supposed to. It's the row meson. Okay? Same thing happened for KK bar mixing. The charm comes in at exactly the place it's supposed to come in, not to give you enormous contributions to KK bar mixing. So these are three instances in the last century where where similar problems came up and they were solved in this way. But as Michael said, really almost from day one, but starting to get serious around LEP, we've had the problem that the new physics has not shown up at the parametrically larger length scales or lower energies than it should have, in the sense that it has in the past. And so if we just think about it for a second, we've gotten so used to the idea that there should be supersymmetry at the TeV scale, but this is supposed to be a theory for W and Z masses, which are down at 80 and 90 GeV. This number of a TeV, which has been creeping up year after year after year, the TeV is really the analog of the, or 500 GeV for the stop, 400 GeV for the stop. It's really the analog of having something come in right at the classical electron radius. It could have shown up earlier. All these hints right from 1980, right, as people started thinking about trying to solve the hierarchy problem, immediately, if there's lots of new stuff at the TeV, there should be all these operators for flavor, EDMs, at the TeV scale, which we hadn't seen. Again, if such was the desire, and so strong was this picture that naturalness would be correct, that all of those things were thought of as not problems, but opportunities. We would learn something about the structure. There would be some special structure, something interesting happening at the TeV that solved all of these problems. So the idea of this idea of naturalness has been really essentially under pressure right from the start, and it's getting under more and more and more pressure as we proceed. But it is not dead yet. It is not dead yet, as I mentioned. As I mentioned before, and we have other precedents for things showing up at the 11th and a half hour. So, so my attitude is that it's either it's still essentially natural. Oh, and I should also say that, to my mind, the 125 GeV Higgs is basically supersymmetry. One reason I say that, I mean, it's true that little Higgses and composite Higgses and other things are not ruled out. I certainly agree that the parameter space has not been studied as much. I agree with all of that. But at least to my mind, a composite Higgs does not want to be something as light as 125 GeV. 300 GeV Higgs would have thrilled composite Higgs model builders. 125 G Higgs, I don't think thrills any of them. Something in the neighborhood of the Z mass is what you expect from supersymmetry. And that's what's so odd and fascinating about 125. Just close to the Z, just close enough to the Z to smell like supersymmetry, just far enough away to put this idea of a natural theory under really increasingly intense pressure. So I don't know myself. I mean, I really vacillate a lot. But I think now it's either something natural but relatively elaborate, and if that's what's going on, we're going to have an infinite amount of fun figuring it out once we actually start producing the relevant particles, or it's some unnatural version of supersymmetry, which is what I think when I'm thinking more simple thoughts and more straightforward thoughts. And unnatural versions of supersymmetry, where the bottom of the spectrum is in the neighborhood of the TeV scale, perhaps motivated by dark matter, but the top of the spectrum is separated by a loop factor, which is a ubiquitously happens in actual theories of supersymmetry breaking. This is something that wants to have the Higgs at 125. You don't have to fight it. That's just where it wants to be. And of course, it means that we won't discover any scalars at the LHC. We may discover the bottom of the spectrum. The problem is it's not guaranteed. But we may discover the bottom of the spectrum. This is why naturalness was so important, by the way, as the real motivation for tons of physics at the LHC. Often people invoke dark matter as another motivation for something at the LHC. But putting aside the fact that there could be other sources of dark matter, even the standard WIMP paradigm, the famous WIMP miracle, does not mean weakly interacting particles at hundreds of GeV. The WIMP miracle, if you just take the W and Z, ordinary standard model interactions, doublets, triplets, simple particles charged under it, compute the relic abundance, go through the early universe, what you need is a 1 TeV doublet, a 2.5 TeV triplet, not particles in the hundreds of GeV range. So that is a distinct possibility. There even may be weak scale dark matter, and the bottom of the spectrum might just be heavy. It might be heavy. It's not guaranteed that we'll see them at the LHC. Nor is it guaranteed that we won't see them. But in this not unnatural picture, I think something that looks much more sparse and a little bit more like what's been going on so far is actually reasonable. And so I'll say again, it hasn't broken for me. If it was 135 GeV Higgs, I would be much more convinced it's unnatural. If it was 115 GeV Higgs, I'd be much more convinced that it's relatively natural. It still wouldn't have been awesome, but I would have been much, much more convinced. That's why the agony goes on.
So in summary, 125 Higgs equals supersymmetry.
Yeah, I think 125 GeV Higgs is some version of supersymmetry from the grand Planck scale point of view.
Can I just get that clarified, because that is such a striking statement. In fact, give many of us hope even to know that our children would find it, you know? I think we got to think like that in particle physics, right? I mean, the scale is not on human terms.